So we've talked about continuity before, but continuity in the most general term means you don't pick up your pencil. And we described that again before. And so I've got three examples down below. I've got a graph of F, a graph of G, and a graph of H. Which one of those three graphs is continuous? H, because on F, you'd have to pick up your pencil because there's that big jump in the middle. And G, there's a hole. But H, it's a continuous graph. You could keep your pencil on the paper and go do the whole thing. And so just looking at it, that's easy. H is continuous. But we have to be able to talk about that in math terms. And so for us, when we talk about continuity, it's made up of three parts. And we're talking about continuity at a point. So like at 2, this graph is continuous. Right? For this F graph, it is not continuous at 3. That's what we're describing. So in order to be continuous, it's made up of three parts. You must have a limit. So that means both sides of the graph have to be approaching the same number. You must have a limit. You must have a value. And so a value means that there has to be some sort of closed circle. There has to be a point there. So for graph G, there isn't a value, so that's why it fails. You must have a limit. You must have a value. And the third part is the limit must be equal to the value. That is the true definition of continuity. You have to have a limit, you have to have a value, and the two things have to be equal to each other. And we could describe it that way all the time, but I have found that it's even easier to describe it in these three terms. In order for something to be continuous, you have to have a limit. Well, how do you have a limit? You have a limit if the left-hand side and the right-hand side are equal to each other. If you have the limit from the left and the limit to the right be equal to each other, that's a limit. How do you find the value? You look at that spot. So like at h of -1, that will tell you the value. So these two things are telling you the limit. This thing right here has to tell you the value. And if all three of these things are equal to each other, then you're going to be continuous. So looking at this graph right here, we're doing it at -1. So I really only care about this spot right here. Here's -1. What is the limit going to be at -1? What are you approaching from the left-hand side? As I go from the left-hand side, what am I getting closer to? 3. As I approach -1 from the right-hand side, what am I getting closer to? 3. The value, or in other words, what is the closed dot? Is there a closed dot at -1? Yeah, it's right there. It is 3. Are all three of those things equal to each other? Then it's continuous. The left, the middle, and the right need to be all equal to each other. If they are, it's continuous. So putting that thing into practice, let's look at the first one, f of x. We are looking at 3. That is where we're trying to determine, is it continuous at 3? So we're looking right here. Ashley, what's the limit as x approaches 3 from the left-hand side going to be? From the left-hand side, it's 3. She's doing this. Audrey H., what's the limit as x approaches 3 from the right-hand side going to be? -2. She's approaching it this way. It's -2. Right now, I could stop. Is this thing continuous? No, it's not continuous. Why is it not continuous? They're not equal, and if they're not equal, that means they don't have there's no limit here. The left and the right-hand side are not equal to each other. There's no limit. We could find f of 3. F of 3 is -2 because you got this closed dot right there. But because they're not all equal to each other, it's not continuous. Do the same thing on g of x. See what you can do. Zach, what's the limit as x approaches 2 from the left-hand side here? It's 2. What about x from the right-hand side? It's also 2. When he's going this way, he's going that way. It's 2. What about g of 2? It's undefined. It's undefined. It does not exist. And so because it is undefined, it doesn't exist. Is this thing continuous? No. You have to have a limit. Oh, we have a limit. The limit's 2. You have to have a value. We don't even have a value here, so they can't be equal to each other. There's no value. Therefore, it's not continuous. Makes sense on how we're describing continuity. It's easy to see. Putting it into words makes it a little bit tougher. But again, the key is left, middle, and right. If the left, middle, and the right are equal to each other, you're continuous. If not, then it's not. All right, so the first one, is f of x continuous at 3? If this were the AP exam, we would want to write out the limit as x approaches 3 from the left, the limit as x approaches 3 from the right, and the f of 3 equals. I understand that you don't want to do that for each one, but let's try one more here together. Limit as x approaches 3 from the left, f of 3, and the limit as x approaches 3 from the right. I always like to put them in order, left, middle, right. Helps me understand it better. And so we're just doing that, looking at the graph. Looking at 3 right here. Does it look continuous? Do you have to pick up your pencil? Yeah, you pick up your pencil. The answer is no. It's not continuous. Because you picked up your pencil. You had to make that dot right there. But we can show that it's not continuous by doing these values. So, Amanda, what is the limit as x approaches 3 from the left? It's 0 because we're getting closer and closer to 0. Aisha, what's the limit as x approaches 3 from the right going to get me? No, you're good. I skipped one. Yeah, limit as x approaches 3 from the right is 0 as well. But what is f of 3? It's -1. F of 3 is -1. That's this dot right here. Because that dot is not up where the limit is, it's not continuous. Make sense? Do the other two. Thumbs up on 0. Is it continuous, yes or no? Thumbs up. Is it continuous at 0? We're getting a lot of yeses. Kate, why do you think it's continuous at 0? The 1. They're all equal to each other. The left of 1, the right of 1, and at 1, they're all equal to each other, so it's continuous. Is it continuous at -2? Thumbs up, thumbs down. Not continuous. Gracie, why not? They're not all equal. What is the left-hand side they're going to get you? 2. What about the value? 2. And the right side? -1. She's going this way. She's got that thing, but down here, she's down that direction. So these two are equal, but that one's not. And so the limit doesn't exist. We failed. Questions there? This next part, we had a little bit of issues with the last period. You can be continuous on an endpoint. Remember, you can find a limit on an end. All right, so for example, let's do the first one. Is it continuous at 0? Well, 0 is the end point. I don't have anything left of 0. What is the limit? If I just asked you, what is the limit as x approaches 0? What is the limit as x approaches 0 going to get you? It's 1. It doesn't have a right side, but that's okay. I'm sorry, a left side. I can get closer and closer to 1 here as I get closer and closer to 0. There's nothing over here. That doesn't mean it doesn't have a limit. All right, it's an endpoint. Endpoints can be one-sided. And so that is 1. In order for this to be continuous, that needs to be equal to f of 0. What is f of 0 going to get you? 2. So is 1 equal to 2? No. So is it continuous at 0? No. Do the next two. Audrey G., what do you think? Continuous at 4? Yep. Why is that? Yep. Approaching this spot here, and you got a point there. It's continuous. So the limit is equal to the value. We're good. Brett, what about at 2? Is it continuous at 2?
Yeah.
Yeah? Why? They're all equal. When you say all of them, what do you mean by all? The left, the limit as x approaches 2 from the left. The limit as x approaches 2 from the right. Is that all you need? And f of 2. All 3 of these things are equal to each other, f of x. Those all 3 things are equal to each other, therefore the thing is continuous. Questions there? Good, we're almost done. Really just one more section left and we're done. Flip it to the back side, one more part. These are just math things you need to know, and so we kind of expect you to know all this, and you should. Polynomial functions are continuous. You have to remember what a polynomial is. Remember, a polynomial is things with exponents that are whole positive numbers. So like 1, 0, 5, 9. If it had a negative, it's not a polynomial. If it had a decimal, it's not a polynomial. If it's a fraction, it's not a polynomial. If it is a polynomial, it's continuous everywhere. Rational functions are continuous at all points in the domain. So we did a whole chapter over rationals. Rationals are just polynomials that are written in fraction form, more or less. Where is this function continuous right now? So given this function, where do we know that it's continuous? All real numbers, but x cannot be equal to what? Plus or minus 2. Why? Why is it not continuous at plus or minus 2? It could be a whole or an asymptote. Either one. I really don't care if it's what it is. It doesn't matter. They're both not continuous. If it's a whole or if it's an asymptote, it's not continuous. Absolute value function. Show me with your arms. What's an absolute value function look like? It's a V. Did you have to separate your shoulder and remove your arm from your body? No, then it's continuous. All right, your arms continue going in both directions. It's a V. Absolute value functions are continuous. That's the worst V I've ever made in my life. Absolute values and calculus don't mix very well. There's not great math with absolute value questions. Normally, if they give you an absolute value question, the best thing for you to do is to make a graph of it. And so keep that in mind in everything we do. If you look at it and you're like, ooh, that's absolute value, let's make a graph and see what's happening. That's probably your best answer like 80% of the time. Exponential, logarithmic, and trigonometric functions are continuous at every point in their domain. So square root of x minus 3, show them with your arm. What's that look like? That's a teapot graph. That teapot is continuous for everything in the domain. And so what's the domain of that? Well, x is going to be greater than or equal to 3. Remember, that's a graph. It shifted to the right 3 because it says minus 3, and then it's a teapot graph from there. There's nothing on the left-hand side, but everywhere from 3 on, we're continuous. Last one is composite functions. If each individual function is continuous at a point, then their composite is continuous at a point. Is a sine curve continuous? Yeah, it's the cool squiggly line thing. X squared minus 3, is a parabola continuous? Yeah. So is it continuous at that point? Yeah, because the other two things are continuous, so that thing's continuous as well. Yeah. You can have different types of discontinuities. You don't have to be perfect at these words. They don't happen a lot. Every once in a while, they'll say removable discontinuity in the problem. But other than that, they're pretty straightforward. A jump discontinuity is just like it sounds. You've got a graph, and then all of a sudden, it jumps up above. Infinite discontinuity. It's going towards infinity on both sides. They don't reach each other. The next one is called oscillating discontinuity. This one's a little bit probably the most rare out of each of them. You start getting these points. It looks kind of like it's continuous, but it's not. If you graph this in your calculator and your thing just starts going back and forth like that, it's because it's jumping values in there. It is not continuous. And the fourth one's the one we care about the most, removable discontinuity. All right? It looks pretty continuous, but there's this one little spot right here in the middle that makes it not continuous. What happens if you took a dot and all of a sudden you put it right there? Is it continuous? Yeah, we removed the discontinuity. They removed it. There's a hole in that thing. That's why it's referred to as removable discontinuity. Those are the ones we're going to focus on the most. Find a value of k to make f of x continuous at x equals 2. Or in other words, we are going to remove the hole. In order for this thing to be continuous, what has to be true about the function in order for it to be continuous? What did we do on the whole front side? There has to be a limit. There has to be and they have to be super. Great job. The limit, a value, and they're equal to each other. Which one of these equations up here is going to find us the limit? Only the top one, because I want to know what's happening when x is not equal to 2. And so to find the limit as x approaches 2, I'm going to use that top equation, that x squared plus x minus 6 equation over x minus 2. That thing right there is going to find me the limit. Cool. Which equation is going to find me the value? The first one or the second one? The second one, because it's telling me what happens at 2. That's the value. I want to know what is happening at 2. So the limit is that one. Limit, I know I wrote it above, but it looks weird. limit, and the value. How do I find the value? I just plug into that super cool equation that's just k. In order for this thing to be continuous, what needs to be true about these two equations? They need to be equal to each other. If the limit is equal to the value, then I've succeeded. All right, cool. I'm going to find the limit. Well, how do I find the limit? I plug 2 in and I see what I get. Oh no, I get 0 over 0. If I get 0 over 0, how do I find the limit? What do I need to do, Drew? Factor? What's the top going to factor into? X minus 2, x plus 3. On bottom, I got x minus 2. I factored, then what? Cancel, and then what? Plug in 2. Factor, cancel, plug back in. 2 plus 3 is 5. Guess what you want the k value be in order for this to be continuous? 5. K is equal to 5. That's the answer to this question. You had this cool graph. Oh no, there was a hole in the middle. How do I fill in that hole? By finding that k value of 5. If I put in a k value of 5, all of a sudden it's a continuous graph again. Let's look at the next one. X squared minus k and 4x plus 2k. X is less than 5, x is greater than or equal to 5. Everybody see what's happening? We are trying to find the k value that will make this thing continuous. In order to be continuous, you need to have a limit, you need to have a value, and they need to be equal to each other. How can I find the limit given this equation? Which one of those two equations do I need to use in order to find the limit? Both of them. Because in order to have a limit, I need to know what's happening on the left-hand side and what's happening on the right-hand side. So the limit, as x approaches 5 from the left, needs to be equal to the limit as x approaches 5 from the right. Those two things need to be equal, and the value also needs to be equal. Which equation is going to tell me the value? The bottom one, because it says it's equal to. Well, cool, it's already built in. If I find the limit, then it's going to be continuous. Okay? So, my equation for this one is x squared minus k. For this one, it's 4x plus 2k. And I want to know what k is. Let me show you what we are doing with this. Here's what's happening. You've got these two graphs. The red graph is the parabola, that x squared minus k graph. The green graph is the 4x plus 2k graph. We are trying to find the k value that is going to make it continuous. Right now, is this thing continuous? No, I want to make them continue. Up, right in there. Okay? Now it's continuous because both sides are getting closer to each other and the values equal to each other. Does that make sense, what we're doing with this? So what can I do with both of these equations? Set them equal to each other. Add 5 in, because to find a limit, we do direct substitution. So it's going to be 5 squared minus k equals 4 times 5 plus 2k. Solve for k. Go. Show me with your fingers what's your answer. Got some 5/3 looking answers. Let's see. This is 25 minus k equals 20 plus 2k. Subtract 20, add k, divide by 3, divide by 3. Oh, cool, it's 5/3. Let's double check looking at my picture. If I change my k equal to 5/3, 5/3. Oh yeah, that looks like they connect right there. Now it's a continuous graph. From the left-hand side and the right-hand side, they're equal to each other. Make sense? Do the last one, please. In order to find the limit, what has to be true here? What do I need to do with both sides here, Lester, in order to find a limit?
Go from, or use like the top equation, or limit is
Approaches from the left, so limit as x approaches 3 from the left, and limit as x approaches 3 from the right. You said this one is the... Yep. And what do I need to do with these two equations? Set them equal to each other. In order to have a limit, they need to be equal. And so he's going to set them equal and plug in his x value. That's a k. 6 plus 9 equals negative 12 plus k. Add 12. 15 plus 12. 27 is K. Make sure it makes sense on our picture. Here's our picture. Right now, they're not continuous. They're not continuous. We got to go this way. That's not even close to being big enough. But if I change that to be 27, now all of a sudden they're on top of each other, just like we thought they were going to be.